Hello everyone, welcome back to another video. So today we will discuss editorial for weekly contest 393 and I was able to solve first three problems only. So we will discuss solutions to first three problems. So first problem. So this problem is basically an implementation problem. So what we are given is an 12-hour time such formatted as hh dot mm. So hh means current hour and mm means minutes, and 12-hour system is valid when the value of hh is from 00 to 11 and mm is 00 to 59. And in this string we are also given some question marks, so we have to replace that question mark such that this is a valid 12-hour format, and also the time it represents should be latest possible. For example, in this case, uh, one question mark, then question mark, and 4. So we can represent it as 10.54 and also represent it as 11.54, but answer here is 11.54 because it is latest. So we have to print a valid 12-hour format and also the latest possible. Similarly here answer is 0959. So let's just see the code. This is an implementation problem. So what I did here is I just compared all the times possible, and maximum number of times possible will be 1200, but maximum possible answer will be 1159, but I just took 1200. But I have written conditions after that which will check for validity of R format. First of all, I'm removing that dot between and converting into a continuous string. Then what I'm doing is I'm iterating from 1200 to 0, and I'm taking s3 string, converting that integer to string, and uh, while the length of that string is less than 4, I'm adding 0 at the start of string. So if I just convert 0 to string, it will be of length 1 with 1 0, but in for the time format I have to make it 0 0 0 0. So to make converting that length from 1 to 4, what I'm doing is I'm writing this for loop, and then I'm comparing both the strings such that if both of them are equal, that means both of them are digits, we cannot do anything about them. And if both of them are not equal, if the original string has question mark in it, uh, then we can replace that question mark. But if they are unequal and both of them are digits, that means we cannot make them equal. So I'm just making cnt equal to 0. Here cnt just a boolean, and for checking the hour and minute are valid or not, I'm calculating the hours here and minutes here. And if the cnt boolean is 1 and d is less than equal to 11 and d2 is less than equal to 59, I'm just printing that result. So this was first question, very implementation based problem. So next question is maximum prime difference. So in this question we are given vector nums, and we have to return an integer that is maximum distance between two indices such that elements on that indices are prime numbers, and the indices are not necessarily different, they can be equal also. So for example here in array 4 2 5 9 5 3, what are prime numbers? This is one of the prime number. Again 5 is prime number and 3 is prime number. So what will be the maximum difference between indices? It will be 1 and this 4. So 4 minus 1. So answer here is 3. In this second case, 4823, 4828. So there is only one prime number. So answer here is 2 minus 2. 2 is the index of that element and 0. And it is given that there is always a prime number in array nums. So in simple terms, answer here will be the difference between indices of leftmost prime number and rightmost prime number, because that will always give you maximum different indices difference. So what we have to do is first calculate first prime number from left, then calculate index of first prime number from left, then find the index of prime number from last, and just print the difference between them. And as you can see, constraints, here it is 3 into 10 raised to power 5, and to check if a number is prime or not, we can find it in square root of n, where n is the number. So complexity comes out to be 3 into 10 raised to power 6, which should not give TLE. So what I'm doing is I'm writing two for loops, and in each for loop I'm starting from one of the end of array and checking if the current number is prime or not. If current number is prime, then I will store that index in CNT and break. Similarly, I'm doing this from right side and finally returning CNT2 minus CNT. So CNT2 is rightmost index, CNT is leftmost index. Now we don't have to worry about when both of them are minus 1, because there is no such condition where there is no prime numbers in the array. So this again second question, if you know some how to calculate, how to find prime numbers, you will be able to solve this. Now third question was somewhat non-standard question, that's why only 700 solutions participants were able to solve it. So in this case, in this question we are given an array representing coins and integer k, and we have infinite number of coins of each denomination. However, you are not allowed to combine coins of different combinations, and we have to return kth smallest coins. So let's just see first example. In first example, we are given array coins as 3, 6 and 9, and in similarly k given is 3. So we can only use a single type of coin in for making what we can say, making a number. For example, we can only use 3, but we cannot combine 3 and 6 to make an amount. So from 3 what I can get is 3, 6, 9, 12, and this will continue up to infinity. From 6 what I can get 6, 12, 18, and this will continue up to infinity. And from 9 I will get 9, 18, 27, and this will continue up to infinity. Now if we put all these numbers in a set, what our set will look like: 3, 6, 9, then again 12, and up to infinity. Now we have to find, in this set we have to find third element, so this third element, and our answer is 9. So in simple terms, what we have to do, we have to find all the possible amounts we can form from this array and the minimum kth element we have to return. So here it was 9. In similarly, let's say from 2 comma 5, what we can make, we can make from 2, we can make 2 4 6 8 10 12 and 14 up to infinity, and from 5 I can make 5 10 15 up to infinity. Now again, if I make set and sort them, my set will look like 2 5 2 4 5 6 8 10, then 12 14 and 15, and k here was 7. So finding seventh least element 12, and answer here is 12. Now how it is important to understand these constraints also. Constraints are very low. Coins length is 15 and coins of I is less than equal to 25. Now if you see those constraints, you kind of feel like a bit masking is involved in this question. But before bit masking, there should be something you should understand. And whenever we are given this type of infinite number of coins, always try to find reverse engineer this question. So what what we, let's say my answer is 9, and if for k equal to 3, my answer is 9. That means before 9, means from 1 to 9, there should be 3 number of elements such that x mod any of the what we can say, any of a of I from any of the coins should be equal to 0. So from 1 to 9, there should be 3 elements such that they are divisible by one of the one of the element of coins. For example, in this case, 1 2 3 4 5 6 7 and 8 and 9. Here I have found that there are 3 elements which are divisible by 3 or 6 or 9. So any of one of the element in coins. Similarly, in this case, if 12 was my answer, that means before 12, from 1 to 12, there should be 7 elements which are divisible by one of the coins. So from 1 to, let's just write them, 11 and 12. So first of all the divisors of 2, 2 4 6 8 10 and 12, and for 5, this 5, I don't need to mark 10 again because I have already marked it. So I found that there are 7 elements. That's why 12 was my answer. So if I can reverse engineer the question like this, I can fix this. And also it is important to understand, if the number of elements before 12 that are divisible by one of the coins of array is 7. So for 13 also it will be greater than equal to 7. For 14 it will be in simple terms 8, but greater than equal to 7, because this is an monotonic function. So it will keep increasing as x increases, as the answer increases. So we can first observation is we can reverse engineer the solution. Second observation is, as x increases, the number of such answer, what we can say, the number of divisors of one of number of multiples of one of the coin also increases. So we can use binary search. So let's say we fix an value answer. Let's say we fix a number and we have to calculate if this number satisfies the k condition, that is there are k multiples of exactly k multiples of uh, one of the coins of the array. Now how to find that there are k multiples? So for that, let's see one example. 369, and I have to calculate multiples of 9. So first of all, what I'll do, I will calculate multiples of 3 in 9. That will be 3. You can just calculate it by finding the floor of 9 by 3, which is 3. 9 by 6, it will be 1.5, but floor, we have to take floor, and then 1, and then 1. So we got multiples. Now this is definitely wrong answer, because sum of this is 5, but our multiples are only 3, because there are some overlapping multiples. When overlapping multiples of 3 and 6, and also overlapping multiples of 3 and 9, because um, while calculating multiples of 3 we considered 3, 6, 9, and while calculating multiples of 6 we again considered 9, and here considered 6, here considered 9. So there is a repetition of multiples. Now how can we remove this? So the number of multiples repeated in 3 and 6 will be equal to multiples of LCM of 3 and 6. So LCM of 3 and 6 is 6, and 9 by 6 is 1. So this one multiple was repeated. So I will calculate multiples of LCM of 3 and 6 and subtract them from this 5. Similarly, I will calculate the LCM of 3 and 9 and subtract them from this 5. Now we subtracted two elements, so we got 3. But there is also a possibility that while removing this, we removed with let's say there was something like 18 in the answer. Here it is not, but let's say our 9 was greater than equal to 18. While calculating LCM of 3 and 6, I also removed one count of 18, because 18 is divisible by 6. LCM of 3 and 6 is 6. And while considering 3 and 9, I also removed 18. I removed 18 twice. So to make that what we can say valid, or make it correct, I have to add that occurrence of 18 once again. So what I have to do, I have to add all the multiples of LCM of 3, 6, 9 into the current answer. So here you can see a pattern where when we consider LCM of even odd number of elements, we add that multiple, but when we consider even number of elements, we subtract the multiples. So this is the concept of the question. For better understanding, let's take one more example. So I have 3, 6, 9, and let's say answer here we have to check for 18. So first of all, I will add this step as 1, where I'm just considering one of the coins. So this is first step. Now I have to add multiples of each element. So from 18 to 3, I will add 6. From 18, multiples of 6 in 18 are 3, multiples of 9 in 18 are 2. Now here answer comes out to be 6 plus 3, 9 and 11. Now again, as we discussed earlier, we added LCM of 3 and 6, that means 6 twice. So I have to subtract, this is second step, where I have to subtract LCM of 3 and 6, and again subtract LCM of 6 and 9, and subtract LCM of 3 and 9, multiples of that LCM. So LCM of 3 and 6 is 6. So multiples of 3 and 6 are what we can say, multiples of 3 and 6. LCM of 3 and 6 is 6, and multiples of 6 in 18 are 3. So I have to subtract 3. LCM of 6 and 9 is I think 18. I have to subtract 1. And LCM of 3 and 9 is 9. Multiples of 9 in 18 are 2. So I subtracted this. Now what I got? I got answer as 5. Now there is again third step where we add LCM of all elements. So LCM of 3, 6, 9. LCM of 3, 6, 9 is 18. Yes, LCM of 3, 6, 9 is 18, and so as we are at odd step, we add 1. So our answer comes out to be 6. Now let's just verify. So I will write all the numbers from 1, 2, 3, 9, 10, 11. Now what we have to find? We have to find all the multiples of 3, 6, 9. So for first 3, I will mark this 3, 6, 9, 12, 15, and 18. Now for 6, 6 is already marked, 12 is also marked, 18 also marked. For 9, 9 is marked, 18 is marked. So there are 6 marked elements. So answer here is 6. And by doing this process, we also got 6. So this principle is called as inclusion exclusion principle, and this can be done with bit masking. So basically we are fixing the elements which we are choosing. So here I choose only 6, only 3 in first step, only 6 in second, in first step, second part, in third part I only choose 9. Similarly for second step, I have to choose 2 elements. First I choose 1, 3 and 6, then 6 and 9, and then 3 and 9. So we can represent this type of choices with bit masking. So if I have to only choose one, I will represent it as 1. So I choose 3, not choose 6, and not choose 9. Similarly, if I have to choose 3 and 6, I can represent this by 1 0 and 1 1 0. So I choose 3, I choose 6, but not 0. And if I choose all of them, I can represent it by 1 1 1. So maximum value here comes out to be 2 raised to power 3 minus 1. I think it is 7. So, and in worst case it comes out to be 2 raised to power 15 minus 1, because that is the coin's length. This is, I think, doable. So let me just find it. So 3 to 7, 6, 7, and for what? Yeah, and additional n for taking iterating over the string or a number itself. And on this there is an log 118 while loop for binary search. So this comes out to be complexity, and let's just see the code then for better understanding. So what I'm doing is I'm declaring low and high for my binary search and answer as 118 first, and I'm calculating the size of array as storing it in n, and then this is complete binary search, I think, till this. and first I'm calculating the mid. So total number of elements in total number of elements from 1 to m will be equal to m, and I'm declaring raise equal to 0 for storing the multiple. Now I'm iterating from 1 to 2 raised to power n minus 1. So I don't have that condition where I'm not choosing any one of them, so I have to remove that. And then what I'm doing is I'm calculating the number of ones in it and finding a multiplication. For storing the LCM, I'm declared a mul equal to 1, and then I'm iterating over all the bits, and if any of them is set to 1, what I'm doing is I'm taking LCM of mul to a of k. Now if p mod 2 is 1, as we say, discussed here, if it is odd, I have to add the number of multiples, and if it is even, I have to subtract the number of multiples. Now if after this for loop, I'm just writing the basic conditions for binary search. If raise is less than k, I will declare low equal to m plus 1, and if raise is greater than equal to k, as I have to find minimum, I will store the current local minimum and go towards left side and finally return the answer. So this was a pretty good question, I would say. If you want to solve similar question, there is a question called as, so this is the similar question. Count GCDs use the same type of inclusion exclusion principle. So if you are interested, you can solve this. And fourth question, I tried this with DP, but I think there is there is some logic for optimization of this question. I used segment tree plus DP, but couldn't solve it. Still, my rank is good enough, I think. So yeah, that's it from my side, and thank you for watching.